Welcome to this explainer. I am so thrilled to have you here today. We're going to take some deeply fascinating, maybe a little abstract physics concepts and translate them into intuitive reality right before your eyes. Seriously, this is going to completely transform how you view the moving world around you.
Think about this for a second. Every conversation you've ever had, every song you've jammed to, every text or video transmitted to your phone, all of our communication basically depends on the invisible power of waves. Human speech, that's just the production of waves in the air. Hearing, that's simply our brains detecting them. We are literally entirely reliant on this invisible force. Okay, let's dive into this. Here's our roadmap for today. First, the nature of waves. Second, categorizing wave types. Third, the anatomy of a wave. Fourth, when waves collide. Fifth, boundaries and standing waves. And finally, number 6, the phenomenon of beats.
Let's start right off with Section 1, the nature of waves, energy and motion. So instead of looking at a single object in isolation, we are exploring collective motion here. Picture dropping a little pebble into a perfectly still pond. What happens? Well, you instantly see those circular ripples rapidly moving outward, right? But here's the trick. If you put tiny pieces of cork on that disturbed surface, you'll notice the cork just bobs straight up and down. It doesn't actually move away from the center. The mass of water itself isn't actually flowing outward with those circles.
So, the crucial point is this. A wave is a pattern that moves without the actual physical transfer or flow of matter as a whole. Waves transfer energy and information. It's exactly like human speech traveling through a room. You can hear someone across the room without them having to blow a massive gust of wind from their mouth to your ear.
Moving smoothly on to Section 2, categorizing wave types, the wave zoo.
Since not all waves behave the exact same way, we first classify them by their direction of motion. In a transverse wave, the medium oscillates perpendicular to the direction the wave is traveling. Just picture giving a long string a single up and down jerk. Now, in a longitudinal wave, the constituents oscillate parallel to the wave's propagation. A brilliant analogy for this is a stationary train. If the engine suddenly pushes the first bogie, that push gets transmitted straight down the tracks through the spring couplings from bogie to bogie without the entire train bodily moving forward all at once.
Now, we also group waves into 3 massive families. First up, mechanical waves. These require a physical medium to travel through, like the water or sound waves we just talked about. Second, electromagnetic waves. These are wild because they don't require a medium at all. They can literally travel through the pure vacuum of space. And third, matter waves. These pop up in the abstract realm of quantum mechanics, mostly associated with particles like electrons and atoms. But for our explainer today, we're heavily focused on those mechanical waves.
But hey, before we move on, I just have to throw this number at you. 299,792,458 meters per second. That is the exact speed that electromagnetic waves, like starlight from hundreds of light years away, travel through a pure vacuum. Put that into perspective, it is truly awe-inspiring.
Let's move to Section 3 and see how this all builds. Anatomy of a wave. Translating the math.
Okay, let's translate some of this dense math into digestible bites. Amplitude, represented by the letter A, is simply the maximum displacement of the medium from its resting equilibrium position. Basically, it's the maximum height of a wave's crest. Phase, on the other hand, is the argument of the sine function in our traveling wave equation. It determines exactly where we are in the cycle at any given position and instant in time.
Next, we've got the spatial dimensions of the wave's anatomy. The wavelength, denoted by the Greek letter lambda, is the minimum physical distance between 2 repeating points, like measuring from crest to crest. The angular wave number, or k, is a spatial propagation constant. It essentially tells us how many radians of the wave cycle exist per meter of space.
Finally, let's talk about the time dimension. The period, t, is the exact amount of time it takes for one full oscillation to complete. The frequency, nu, is simply the inverse of that. It measures how many of those full oscillations occur in a single unit of time, like a second.
And this brilliantly illustrates how all these pieces dictate a wave's speed. Notice how the speed of a wave isn't just some random number. It relies entirely on the inertial and elastic properties of its specific medium. For a transverse wave on a string, it's about tension and mass density. For longitudinal sound waves, it comes down to the bulk modulus, which is basically the elasticity of the air, and its density. The medium is what totally determines the speed.
All right, shifting gears. Section 4, when waves collide, the principle of superposition.
So, what happens in the physics of waves when they actually cross paths? I really want you to think about this for a second. If two wave pulses on a string are traveling directly toward each other, what happens the exact moment they hit? Do they bounce off? Do they totally destroy each other? No way. Remarkably, waves actually retain their individual identities after they overlap. They just pass right through one another. But during that overlap, something really special happens.
This is known as the principle of superposition. The net displacement of the medium is simply the algebraic sum of the crossing waves. If the waves are perfectly in phase, their amplitudes add together to create a massive peak. That's constructive interference. But if they are completely out of phase, say where a crest meets a trough, they mathematically subtract and cancel each other out to a net zero displacement, and that is destructive interference.
Which leads us nicely to Section 5, Boundaries and Standing Waves, Trapped Energy.
This brings up a totally logical question: what happens to a wave when it completely runs out of space? Let's walk clearly through the mechanics of wave reflection. When an incident wave hits a rigid, unmoving boundary, like a solid wall, it reflects back, but with a phase reversal, so a crest bounces back as a trough. Interestingly, if the boundary is open and free to move, it reflects without a phase change. Now, when a continuous wave reflects back onto itself, the incoming and outgoing waves constantly superimpose, adding and canceling to create what we call a standing wave.
In these standing waves, we see perfectly stationary patterns. The spots where destructive interference happens constantly are called nodes. These are completely fixed points of zero displacement. On the flip side, the points of maximum constructive interference are antinodes, the points with the absolute largest amplitude. Because the boundary conditions constrain where the nodes must be, systems like stretched guitar strings are locked into vibrating only at very specific, constrained natural frequencies.
And that brings us to our final topic, Section 6, the phenomenon of beats, waxing and waning. Now, what's really interesting here is connecting this complex physics of interference directly to everyday acoustics. When two harmonic sound waves with frequencies that are very close but not exactly equal overlap, they constantly drift in and out of phase. This creates an audibly distinct waxing and waning of sound intensity. It gets louder, then softer, then louder again. These are called beats, and the beat frequency is literally just the mathematical difference between those two original frequencies. Fun fact, musicians use this exact phenomenon every single day to perfectly tune their instruments by ear. Wow, okay, we've gone from dropping a pebble in a pond to calculating the interference of overlapping harmonic oscillations. From the physical strings of a violin to the invisible quantum matter waves of an electron, everything in the universe is vibrating. It's all transferring energy and information through this absolutely incredible mechanism. So I'll leave you with this to ponder. What frequency are you tuned to? Thank you so much for joining me in this explainer, and as always, keep learning.